Hi, welcome to the screencast for section 12.4. 12.4 talks about phase changes, and living in Minnesota, phase changes are something we're familiar with. Substances on Earth exist in one of three states, either a solid, liquid, or a gas. There's actually a fourth state called plasma, but that doesn't exist here on Earth naturally. So we're just going to contain ourselves to the three that are around us. And the state of a substance depends on not just the temperature, but also the pressure. And pressure is one thing you probably haven't thought about a lot before as far as phase changes, because pressure around us usually remains pretty close to the same. Atmospheric pressure changes a little bit day to day, and we have high and low pressure systems moving in, but generally it's about the same. But pressure can have a big effect on the state of matter because pressure can push particles closer together or further apart, just like temperature can give them the energy to move closer together or further apart. So a phase change is when a substance changes from one state to another, and for any phase change, energy must either be added to speed up and spread out molecules, or it has to be removed to slow down and pull them closer together or allow them to move closer together. So energy has to be added or removed, or pressure needs to be increased or decreased. And adding energy tends to speed up and spread out molecules, while adding pressure tends to push them closer. So they have opposite effects. Kinetic molecular theory explains this because as temperature increases, motion of particles increases, and forces of attraction can be overcome. They can either stretch out those forces of attraction, like stretching a rubber band, or you can completely break free from those forces of attraction, like breaking a rubber band. When temperature decreases, then particle motion decreases, and the attractive forces take over and are able to pull them tighter and tighter. In all phase changes, again, the particles either speed up and spread out because energy was put in, or pressure released. I should add that here. And or the other option is that the particles slow down and move together because energy is removed or pressure increased. And of course, it could be a combination of both temperature and pressure changes. So first phase change we're going to look at is freezing or melting. And freezing and melting is changing from solid to liquid or liquid to solid, and they're opposite processes. If you remove energy, you can take a liquid and turn it into a solid. If you add energy, you can take a solid and change it to a liquid. It happens at the same temperature, and most people don't think about that water freezes at 0 degrees, but it also melts at 0 degrees. It's just the opposite process. So when it's 0 degrees outside, how do you know if something's melting or freezing? It's not doing either. It's just slush, because until you actually decrease the temperature below 0 or increase it above 0, it's not going to complete that phase change. So to freeze particles, the particles have to move closer, and the intermolecular forces have to take over so that the molecules no longer have the freedom to move, but vibrate in place, and it has a definite shape and volume. So freezing is a process where energy is released. That's why you put it in the freezer. To melt, the particles stretch further apart, and there isn't enough molecular force to hold the shape, but there's still enough molecular force to keep the volume. So energy is gained in the process of melting. Similarly then, if we look at vaporization, or we commonly call it boiling, the rest of the world calls it vaporizing because it really makes more sense. A liquid is becoming a vapor or a gas, and then condensation is the opposite process. So you could change from liquid to gas or gas to liquid, and again, they're opposite processes. They're going to happen at the same temperature, so water boils at 100 degrees, and it also condenses at 100 degrees. Just like freezing, if you want to condense a vapor into a liquid, the particles have to move closer, so the intermolecular forces have some effect on the molecules, enough to give it a fixed volume, but not enough to give it a shape. So energy is released during condensation. And then to vaporize or boil, the particles need to move so far apart that it actually breaks that intermolecular force. They're too far apart to have an effect on each other. So gases will have no volume and no defined shape. So definitely gaining some energy to vaporize. There's also two other phase changes that we're not as aware of because a lot of substances we don't notice it, but there's something called sublimation and deposition. Sublimation, you've heard of subliminal advertising. Sublimation happens just kind of sublimely around us. We don't really notice it, but it's when a solid goes right to a gas with no observable liquid phase. So dry ice is one of these. It's really what's happening is the substance's melting point and boiling point are so close together that the liquid state is just fleeting, that it's not liquid long enough for us to even observe it. So that's why dry ice appears to go right from a solid to a gas, because its liquid and boiling point are virtually the same thing. And you do see it with other things like solid air fresheners now. You know, you plug them in and they just disappear over time. Or when you have ice in your freezer and the ice cubes get smaller, you're like, where are they going? Or now, this never happens at my house, but if you have ice cream in your freezer with these self-defrosting freezers, it deliberately sublimes or takes any frost that builds up there and removes it as a gas. So sublimation does happen around us. We just don't notice it a lot. Deposition is the opposite then. It's a gas going to a solid with no observable liquid phase. And we do notice this in Minnesota because we see frost on the grass, frost on our windshields. That's deposition. There was no liquid state. It deposits as a solid. In fact, snow would be another example of deposition. So freeze-dried food is when food is frozen in a vacuum so that the water will sublime. Why does a vacuum make it sublime? It's because you've lowered the pressure so much that the boiling point has dropped down very close to zero. So that's why you have to freeze dry in a vacuum to get the water up. And it does that because it makes the water lighter and there's no water that gets in there. You know, there's no liquid state, so it's unable to grow bacteria. This is also why snow disappears even on really cold days, and ice cubes, as I mentioned earlier, shrink in your freezer. Even on cold days, some snow will be able to go right from the solid state to the gas state. Okay, boiling and altitude. Most of you realize that water boils differently when you're up in the mountains or at a higher altitude, and you maybe have noticed on the back of a cake mix or something that they have different cooking instructions. Boiling is affected by atmospheric pressure because the particles in the liquid need enough energy to escape while the surrounding air particles are exerting pressure against them. So the pressure that the particles in the liquid have is called vapor pressure, and the surrounding particles exert atmospheric pressure. And when the vapor pressure is equal to or greater than the atmospheric pressure, that's boiling point. And we see it as bubbles rising up from the bottom because we're usually adding heat to the bottom. And then these bubbles, what's misleading is people think these are air bubbles. They're not. These are bubbles of water vapor. They came from inside of here. There's no air in the bottom of this pan. It's not sucking air in through the bottom. Think about it. This is little bubbles of water gas, okay, water vapor. And when they get to the top, they escape. That's why when enough of these bubbles are around, the level of your pan goes down and down and down. So, this is what I mean about kinetic molecular theory being able to explain all kinds of amazing things around you. People just don't think about what's happening. And when you slow down and think about it and visualize, it's like, hey, I know what's going on and I can explain it to somebody else. So you've got these water bubbles. Water bubbles are going to form at the bottom because that's where there's the greatest heat. So they've got the motion to spread apart. They rise to the surface and those particles escape. So the difference when you're at altitude is there's less pressure because there's fewer particles out here. They're more spread out because they're further from the center of gravity. So it's easier for them to boil and escape. And we'll talk a little more about that later. In fact, I guess right now. It says higher elevation means less atmospheric pressure. So what will happen to the boiling point? Boiling point's easier. There's less air pressure, less holding it down. The pig pile on top of the water got lighter, so it can escape easier. So water boils at a lower temperature in the mountains. But here's the weird thing. What happens to your cooking times? If you look at the back of that cake mix, you actually have to bake your cake longer in the mountains. Now, it's easier to boil, so why do I have to bake it longer? It's because it actually takes longer to cook at high altitude because the water's boiling at a lower temperature. That means your food is also cooking at a lower temperature. And when you cook at a lower temperature, you need more time. So kind of a weird aha there. Okay, here's another strange thing about water and phase changes. To boil 100 grams of water takes a lot more energy than it does to melt 100 grams of water. Now think about it. 100 grams. If I change 100 grams of water into moles of water, that's a little over 5 moles of water. 100 grams of ice is also a little over 5 moles of ice. It's the exact same number of particles. It's lots of them because I'd have to take 5 point whatever times 6.02 times 10 to the 23rd, but it's the exact same number of water particles. So why does it take so much more energy to melt it than it, why does boiling take so much more energy than it does to melt it? It's the same substance, the same mass, the same number of particles to speed up or slow down. Well, here's the difference. Intermolecular forces. When you go from a solid to a liquid state, remember I said the particles speed up and spread out, and the intermolecular forces are stretched like a rubber band. But when you go from a liquid to a gas, now you have to break the rubber band. And we all know it takes a lot more energy to break a rubber band than just to stretch it to its end. So that's the difference, and we'll see it on some graphs here in a little bit. So evaporation, this is another phase change that we don't think about because it just happens naturally around us. It's like boiling because a liquid becomes a gas, but it happens at room temperature. So what makes evaporation different, even though it's a liquid going to gas, is it's a much slower process because it's happening at a lower temperature. The molecules at the surface are the ones that escape to become a vapor. So unlike when you're boiling and you're adding heat to the bottom of the pan, and that's the water that's coming up and escaping, with evaporation, it's the particles at the top. And so if a breeze blows by, those faster moving air particles can hit these surface water particles and give one enough energy to escape. When you're sweating, your body's at 98.7 degrees Fahrenheit. The surrounding temperatures maybe 70, 80 degrees. So you give the water molecules on the surface of your skin extra energy so they escape. And guess where they take that energy? From you, so it cools you off. So evaporation is just an unusual case of boiling at a slower rate and a lower temperature. Okay, so real quickly here, changes that require energy. When do you have to put heat in? When you want to melt, when you want to boil, if it's going to evaporate, or if it's going to sublime. So on a graph, we see these plateaus, and I'm going to scroll down so you can see it. Energy is being added in here. You can't see this line so well, but it's being added in, and then it plateaus at 0 degrees. Then it goes up again, and it plateaus at 100 degrees, and then it takes off again. So what's going on? Well, during this time, you're still adding energy, but the temperature's not going up, so that energy has to be going somewhere else. And where that energy is going is it's going to speed up and spread out all of those particles in a solid formation. Once all the particles have gotten the freedom to move and behave like water or achieve the water phase, then the temperature goes up again. Now the water molecules are getting faster, faster, faster. And now when we hit 100 degrees, this is where water has enough energy to break free of its attractive forces and become a gas or steam. But again, we're going to see this plateau until every water molecule has managed to break free from the attractive force. And like we mentioned before, I've got the same volume of ice and the same volume of water, but it takes a lot longer to get the water all converted over to steam because now I have to break the bond instead of just stretching it. Phase changes that require energy, just the opposite then, condensation, freezing, deposition. I'm just going to scroll down here and you're going to see the opposite chart with the opposite thing happening. During these plateaus, that's when you have both states, both the solid and the liquid or the liquid and a gas. The last thing to talk about are pressure temperature phase diagrams. And these are new probably to you, but it really shows the relationship between pressure and temperature. You can increase temperature and decrease pressure to have the same effect. So when we look at it, the lines on a phase diagram indicate where more than one phase exists or a phase change is occurring. So those would be your boiling point, melting point, etc. And the triple point is where all three states can exist. If you had water's pressure and temperature at exactly the right temperature and pressure, you would have this point A here called the triple point where you'd have some solids, some liquid, and some gas all going on at once. Under our normal conditions, right here, this is about 1 atmosphere, which is pretty much what we live at. Generally, we see water go from a solid to a liquid and a liquid to a gas as temperature increases. So this is kind of what normally happens going left to right. But if we change pressure, we can also affect it. Last thing to wrap up here, here's a graph I'm going to leave you with that kind of indicates when energy is added or removed